Okay, looks it's a goodly number of people here. I'm sure there'll be a few more joining us as time goes on, but let me give everyone a warm welcome to our first NuSec Lunchtime seminar. We thought this would be a good idea to have some talks by people in the community and to keep it fairly lunchtime-ish. Low-key questions and answers, 15 to 20-minute talks. So a good opportunity just to hear what each other are doing and be able to interact with each other a little bit. Obviously, over the past year, we got really tuned into these sorts of things. So hopefully, we'll hit the right balance between not producing too much screen fatigue, but also making the most of our ability to interact with each other these days. See more people still joining us. Welcome, everyone. I think there's probably another bunch of people still to join us, so we'll just give it a moment or two. We've got two good talks today, as you would have seen from the advert. Callum Grove first and Craig Jones second. They've got first talk by Callum on his quantum dot loaded plastic scintillators, and a second one quite different on some modelling of transient nuclear criticality excursions. So a couple of quite different talks, but be really interesting to see what they've got to say. And while we're just waiting for a few more people to come in, let me just draw your attention to the NuSec NNSA collaboration grants. So this was this scheme was launched a few months ago when we had a meeting with the US consortia, which many of you attended. And so this is a scheme that ultimately money was being provided by the STFC, and it's designed for us as a community to develop our collaborative work with the American academic consortia. And those consortia, as you can see on the left-hand side of the screen, we've got NSSC, the Nuclear Science and Security Consortium. And then we've got two others who's MIC and something else, I've forgotten their name. Anyway, but the grants are for projects. The four little squares, the top two squares on the screen, you can do some postdoc projects or some undergraduate projects if you want to. And I emphasize it's a collaborative nature is what we're looking for in these applications. Or you can bid for some money to go and visit them, go to a conference or training as well. And so the maximum sums are all proportional to that. So there's a link there on the screen, nusec.uk/NNSA. I do encourage you to have a look at that and think how you could build up some contacts with the US consortia. The US consortia have got really good websites if you want to try and understand a little bit more about what they're doing, or contact us if you want to learn a little bit more about that. Okay, people still coming in. Welcome everyone. If you just joined, we're just going through a little bit of preamble. So just a warning, everyone, this is being recorded and we hope to make it available on a YouTube stream afterwards, and details will come out about that afterwards a little bit later. So for the purposes of today, if you can keep your microphones off and for the duration of the talks, just to reduce the background noise. I think this is becoming second nature. Everyone's got your mics off already, so thanks very much for that. When it comes to Q&As, then you'll be able to just switch on your mic and your camera will be able to see you and talk, hear your questions. So it's probably about time that we got started. So as I mentioned, two talks today. The first one is Callum. So I'd like to welcome Callum. Thank you, Callum, for making the time and effort to come and give a presentation. So we're thinking 15 to 20-minute presentation, and then Q&As from everyone for a few minutes afterwards before we go into our next talk. Callum, welcome. Are you able to share your screen?
Yep, I'll just share my screen now.
Excellent. Then with that, I'll hand over the floor to you.
Fantastic. Thank you very much. And thank you very much for inviting me. So as Neil said, I'm going to be talking about my PhD project, which is based on quantum dot loaded scintillators for the specific purpose of X-ray luminescence is what we're trying to, but the overall arch is radiation detection for applications in nuclear security. So a brief introduction. So plastic scintillators currently being used in the field that are cheap, but they don't have any gamma resolution, energy resolution. So they don't produce a photopeak, and various loadings have been used, such as lead, to try and up the effective atomic number, but that comes at a cost of reducing the light output. And the idea is that quantum dots will increase the effective Z and therefore increase the photoelectric stopping power while also producing light themselves. And so you end up with a double advantageous gain of loading quantum dots into plastic scintillators. So this talk today, I'm going to discuss briefly about the material that we chose. So we did a investigation of several different quantum dot materials in liquid dispersions, so dispersed in toluene, and compared their emission and absorption characteristics to try and work out what the best properties were for loading into a plastic scintillator, and then selected the best. And we made 3 batches. So the 3 batches, if you can see at the bottom, we have a homogeneous batch, these are part of the same batch, sedimented batch, and then a hybrid batch that has a sedimented layer of highly concentrated quantum dots at the bottom and a homogeneous layer similar to the first batch. And so I'm going to be talking through briefly the casting process and then the early results that came out of it, specifically with respect to X-ray luminescence. So for anyone who doesn't know what quantum dots are, they are essentially nanocrystal semiconductors. So they're typically less than 10 nanometers in size, so the core here, and they generally have a core shell and then ligand structure. So you have a core material which has a band gap which a band gap which is less than the shell, and so you end up with electron confinement within the core. And there you have the shell material surrounding it, which traps electrons in the core material, and therefore they produce emission when electrons are excited and then de-excite and recombine from valence to from conduction to valence. But because of their size, they appear to like artificial atoms, so they have discrete energy levels, and therefore you can tune their emission based on the size of the quantum dot that you have. So a smaller quantum dot will have a bluer emission rather than a larger quantum dot will have a redder emission. And then another thing to do with the structure is that they have these ligands, which are organic molecules that are just attached to the outside of the shell, and they infer solubility within within plastics or other organic materials. So as I said, we had a quantum dot liquid dispersion test. So we dispersed 5 milligrams of these quantum dots into 5 milliliters of toluene, and then we did a emission study using a 405 nanometer blue laser, and then a absorption study using a Curie 5000 spectrometer. So we have various emission maxima that are presented in both the table and the plot on the left here. And ideal quantum dot characteristics that we were looking for loading into, selecting the one to load into a plastic scintillator was bright emission. And so the brightest emission came from our copper indium sulfur with a zinc sulfur shell, compared to the cadmium based cadmium selenium, and then the even dimmer zinc copper indium sulfur. And so the idea was initially that the zinc would increase the band gap and end up with a bluer emission. However, that hasn't been achieved, and it ended up reducing the brightness. I should say that we haven't manufactured these quantum dots on site. These are all commercially available. So at the moment, they're relatively expensive to buy, but if we could start synthesizing them on site for projects outside or after my PhD, the cost of them are going to dramatically decrease. The other thing to notice is that you have the absorption spectrum on this as well. And so there's a significant overlap with the cadmium selenium compared to the cadmium-free samples. And so a difference in absorption maximum and emission maximum produces a Stokes shift. So we have a 20 nanometer, or for those that prefer energy, which is 0.1 EV here, or the cadmium-free and very bright has a 181 nanometer or 1.1 EV Stokes shift. And so you end up with a minimal overlapping in terms of absorption and emission spectrum for this green line here. And so that is beneficial because there's going to be a limited or minimal amount of self-absorption. And so where it won't absorb its own emission, and therefore you can have a good scintillator. So moving on, we selected the bright and high Stokes shift copper indium sulfur for loading into quantum dots, loading into plastic scintillators, sorry. And the idea behind this was that we would take LGen's EJ290, which is a casting resin. So it's a PVT base with a mixture of fluors in a partially polymerized resin. And then you add a catalyst and you can turn it into whatever shape you want, or you can load it with whatever material you want to load it, and then cast it over in a water bath at about 50 degrees over a period of 2 weeks. We were interested in the loading rather than the shape, so we had just centimeter cube molds. And the way that we would cast a scintillator is we'd first dissolve quantum dots into a small amount of toluene. So compared to 5 milligrams to 5 milliliters in the liquid dispersion study, this is a picture of, on the left here, of 40, 80, and 120 milligrams in about a quarter of a milliliter of toluene. So they're quite highly dispersed, and then put that into the mold with the resin and mixed it together, cast it, and produce this at the end of the 2 weeks. So you can see that there's a significant concavity at the top, which is where you had shrinkage when polymerization occurred, which just needed to be cut off the top, which is why we were trying for cubes, but we allowed for extra height. So we cut the top off and then polished them and produced this as an example of the homogeneous batch. So the 3 batches that we have homogeneous, 3 different loadings, 2%, 4%, and 6%. The 4% wasn't as successful. There's a significant clumping of quantum dots on one side of the scintillator rather than relatively well homogeneously dispersed throughout the scintillators as the 2 and 6% are. And then we went on a different tact and try, instead of a homogeneous plastic scintillator, as we'll get to, the results didn't show, someone's at the door. forget about that, sorry. And so we decided to have a highly concentrated sedimented layer at the edge of the sample instead, so that we'd have a very highly altered effective Z in this quantum dot region. And so we did two versions of this. So we had a fully sedimented, as you can see here, which is more or less a clear plastic with quantum dots at the bottom. There's a few quantum dots that had settled throughout the bulk medium on this scintillator here. But generally, the idea was to have it all coalescing at the bottom. And then we went for a hybrid approach where for slightly older resin and therefore thicker resin to start with, so it wouldn't sediment as much as it had occurred here, we'd have a sedimented layer and a homogeneously dispersed region in the bulk crystal. And so they're the three batches that we'll be discussing. So homogeneous, sedimented, and hybrid, so between the two. So we confirmed the loading rather than just saying the quantum dots are yellow, therefore they're in there. We wanted to quantify how much the loading was. And so we did this through energy dispersive X-ray spectroscopy. And so these are example spectra of a sedimented layer and a bulk medium. And so you can see the characteristic X-ray lines from the zinc and specifically the sulfur. So interestingly, we don't get that much core materials. So there's a limited amount of copper and a limited amount of indium that's available. The reason we think is because we're viewing the shell material around the outside of the quantum dots, and the X-ray or electron beam wasn't penetrating the core and producing X-rays well enough. And then the bulk medium on the side here, there's a zinc and sulfur lines, but not anywhere near the same intensity. And so we know that there's a small amount of X-rays, a small amount of quantum dots in the bulk medium. However, it was very hard to measure that in any real quantity. So the EDS system that we used was accurate to about 0.1, 0.2 percentage by weight. And so any quantum dots in around here in the bulk medium are less than what was the resolution of the EDS. But highlights from the X-ray spectroscopy, so the 6% homogeneously loaded sample showed about 3% copper. So interestingly, we didn't see shell elements for the homogeneous, but we did see core elements for the homogeneously loaded. And it's potential that the sedimented layers didn't penetrate the shell, whereas the homogeneously loaded layers did penetrate the shell, and we did see part of the core. And so in this kind of schematic, we'd have half copper and half zinc for every sulfur. And so you'd expect it to be around 3% copper, 3% indium. We didn't really see much indium, but copper suggests that there was quantum dots consistent with what we were expecting. And then the sedimented layers here are pure shell. So zinc at about 16% by weight versus sulfur about 4%. So converting these to atomic weights, that's about 4% zinc and 2% sulfur, which sounds relatively low compared to a back of the envelope calculation for how concentrated the sedimented layers should be. They should be about 20%. However, the reason for this was that there was a high amount of charging that was happening on these plastic scintillators because they're insulators, and so you didn't have very good conduction, and so you didn't see a lot of the characteristic X-rays because the electron beam was being deflected or not producing the X-rays that we were expecting. But then the hybrid sample down below was slightly better in terms of conduction, and so we ended up seeing more in their sedimented layers throughout the sedimented layers. So this is both an average recording for the sedimented layers. So despite there being more quantum dots in the sedimented layers of the sedimented batch, we saw more in the hybrid because the sample itself was more conducting and therefore produced better results. It's also worth noting that this zinc and sulfur share about a 1-to-1 ratio in terms of atoms, which would be consistent with a 1-to-1 ratio of zinc and sulfur, which does suggest that we're seeing the shell and not the core elements. So as I said, that they were an average across the sample, and then this is a line scan across the sample. So there's a significant amount of deviation as we go across the sample for the sedimented layer, a sedimented loading sample. And you can see this in X-ray maps as well. And that's because we developed cracks in the sedimented layer from when it was cut off the side of the sample. And in these cracks, there was a high amount of carbon that was forming, which produces these erroneously high carbon content. Because we coated our samples with carbon to produce a better conduction, compared to the hybrid loaded, where we don't see those cracks as significantly in the X-ray maps. And in fact, the percentage loading increased as you went from left to right across the sample, which, as you can see, is consistent with the sedimented layer itself increasing in thickness. And so what happened was the casting itself was, or the mold within the casting was slightly tilted forward, which we didn't realize to start with. And so a lot of the quantum dots tried to coalesce towards one side of the sedimented layer. So we ended up with thicker and more concentrated right region here. So moving on to experiments on these loaded scintillators. So first I'll talk you through the homogeneously loaded scintillators, and we have a transmission spectrum here. So we have a band gap of the plastic at about 400 or about 405. And then that tails off for the unloaded spectrum, and quite sharply, and you end up with a emission or transmission plateau until about 800, where we have peaks and troughs corresponding to the polyvinyl toluene base absorbing. Whereas in the loaded sample, the plateau doesn't start, transmission plateau doesn't start until about 600, which is consistent with an additional band edge corresponding to the quantum dots absorption. So that was about 480 in these transmission spectrum. So it should also be said, we were expecting the transmission of the unloaded scintillator to be higher. However, when polishing, we ended up polishing more material off these two samples, and so we ended up with an artificially high transmission because we have a smaller sample. Moving on to photoluminescence. So we have the unloaded EJ290, which shows a similar emission spectrum to EJ212, which is what the resin itself is based on. And then when we have loaded plastic scintillators, those peaks have dropped in intensity due to being absorbed by the quantum dots. And then the quantum dots themselves have started or are emitting at 550. And so we end up with this red shift in emission. However, as I said, the intensities themselves dropped off dramatically for the homogeneously loaded, and so we think that the benefit of loading homogeneous is not as high as having an unloaded scintillator, and that's why we went for the sedimented with a highly concentrated layer. And a similar story seen with X-ray luminescence. So the unloaded plastic peaks have dropped in intensity, and there's a shift towards the quantum dots, but there's even less of a shift. So the sedimented loaded scintillators, the transmission themselves dropped off significantly for the top and bottom orientation, so through the sedimented layer, and you have no plastic absorption, but you have this quantum dot absorption only, so that's doing the primary absorption. And then the side orientation through the bulk medium dropped off slightly, indicating some quantum dots, but the shape is not significant. And then photoluminescence for these samples. As you can see, for the top orientation and the bottom orientation, the quantum dot peak is now much or significantly brighter than the unloaded scintillator. And that carries through to the X-ray luminescence, where we have quantum dots absorbing the unloaded peaks and producing a reasonably high emission, which is also significantly higher than an unloaded sample. So
Callum, if I may just interrupt, have you got many slides left?
Should be 3 more slides left just on the hybrid samples. Sorry, I realised I was overrunning, so I'm trying to hurry up a bit.
Yeah, if you can try and summarise a bit, that'd be great.
Yeah. So the similar story for the hybrid loading. So we have a drop in intensity for the transmission, significantly to less than 10%, less than 2%, depending on the orientation. And this is because of the highly loaded and opaque regions in both the bulk and sedimented layers. Photoluminescence, there's hardly any plastic emission, and it's all quantum dot emission, suggesting that all of the plastic is being absorbed by the quantum dots and emitted at the 550 nanometer range. And then a similar story to photoluminescence for X-ray luminescence. However, they're not as bright as the sedimented samples. So if you can compare the y-axis, it's about arbitrary units, but 6 times 10 to the 5 versus 1 times 10 to the 7, or in X-ray luminescence, 7,000 versus about 10,000. And then the homogeneously loaded samples are even smaller at about 2,000 arbitrary units as a integral for the peaks themselves. So overall, what we came to the conclusion that the sedimented loaded plastic scintillators is potentially the best way to go. So the next step will be to try and get a large enough and highly loaded enough scintillator to get a energy resolution out, or potentially just use a thin quantum dot region rather than having the plastic substrate attached to the other side. So sorry for going over, and thank you for listening.
Because I've kind of been aware of what you're doing. Let me give you the floor then, and why don't you take over?
Thanks, Neil. Hi, everyone. Thank you for allowing me to talk here today. I'm going to be talking a little bit about mathematical and computational models for simulating transient nuclear criticality excursions in fissile powder systems with fluid ingress, with a specific focus on aiding emergency planning and preparedness in fabrication, production, and just throughout the fuel life cycle. My main research interests are obviously nuclear criticality safety. Previously, my research has focused on both powder-based and solution-based systems, and I work both on time and spatial dependence in my numerical modeling. So just before going on to a bit more about my work or where we may find powders in the fuel life cycle, I'm just going to discuss a little bit about what criticality safety is. So criticality safety experts are dedicated to prevent inadvertent and self-sustaining nuclear chain reactions. And their assessments essentially ensure that double contingency measures are in place so that for an accident to happen, 2 independent failures would be required. The assessment of risk is usually based on the MAGIC MERV or MERMAIDS acronym, depending on where you're from. So for MAGIC MERV, this stands for mass, absorption, geometry, interaction, concentration, moderation, enrichment, reflection, and volume. And the ultimate aim, obviously, is to prevent accidents from occurring, but if they do occur, there is the International Nuclear Events Scale, which quantifies the severity of an actual accident. So you can see in the image in the top right that the severity varies from 7 to 0, and it's based on a logarithmic scale. To put some accidents to the numbers, the only 2 major accidents, i.e. level 7, that have occurred are Chernobyl and Fukushima. Windscale and 3 Mile Island were both level 5 accidents, for example. So to describe MAGIC MERV in a little bit more detail, if you look at the bottom right image, what I'm trying to represent here is the red represents plutonium and the blue represents water. And the masses underneath represent the critical mass of each configuration. So you can see from the leftmost image that the critical mass of this plutonium sample, which is spherical, in air is 9.9 kilograms. If you then were to pick up that sphere and drop it in water, so you're altering where the leakage of neutrons is going into, in this case it's going into a moderator which can thermalize it and reflect the neutrons back in, the critical mass actually drops to 5.4 kilograms. And then if you were to take the same mass of plutonium and actually grind it up into a powder and pour that into water, the critical mass goes all the way down to 0.5 kilograms, because you have a very homogeneous mixture of water and powder, so that fast neutrons that leave powder particles can actually be thermalized back in to the fissile sample and cause further fission. So powders are found throughout the nuclear fuel life cycle, all the way through from mining and milling through to reprocessing. So milled uranium ore is milled and chemically processed to make yellow cake, which you can see on the right there. And it's low enriched because obviously it's got the natural enrichment of uranium from the ground at about 0.76% or so. So it poses quite a low risk for a nuclear criticality safety assessment. Once the yellow cake is converted usually into UF6, it goes through to the enrichment facility where the uranium is obviously enriched and the portion of U-235 compared to 238 is greater. It's after this stage where a higher risk of a criticality accident happening occurs because obviously it's greater enrichment. Once you've got enriched uranium and you pass it through to the fabrication and processing facility to actually produce your fuel or whatever the purpose is, this is where you tend to see quite a lot of powders, and numerous accidents and potential accidents have occurred in this kind of facility, which I'll describe a little bit later. You can see in the top right here, we've got a conical stirrer of MOX powder. So this is plutonium mixed with uranium, and it's mixed in this stirrer in a dry mix to get a homogeneous mixture before MOX pellets are formed. And this tends to be moderated by a hydrogenous material. There's obviously a criticality safety case where a hole in the stirrer causes the hydrogenous material to enter the stirrer, which can lead to a nuclear criticality excursion. In the image on the bottom, you can see uranium dioxide as a powder, which is then crushed into pellet form in these fabrication and processing facilities. The powder is usually held in these cylindrical vessels. Double contingency measures are usually in place, which entail specifying subcritical packaging limits, whereby if the packaging were to get fully immersed in water, a criticality excursion wouldn't be reached. The other contingency measure is a moderating insert, which is usually that. So you can see in the image in the middle as well, there's a SEM micrograph. On the left, you can see a MOX powder, and in the center and the right, you can see UO2 powder. So that's sort of just to get a view of what the powder looks like up close. So once it's fabricated, obviously, and you've got your fuel pellets, it then goes through to the reactor, into the rods and into the reactor. And once it's then, it gets stored in open air pools until it's cooled enough and the thermal energy being produced by these rods has decayed a bit. And from there, it can go either to nuclear fuel reprocessing or onto dry cask storage. So I'm just going to highlight a couple of the process accidents that have occurred during the precipitation of powders and slurry-based systems pre-2000. So the first one took place at the Mayak facility in Russia, inside a filtrate receiving vessel housed within a glove box that a single operator was working in. In this system, impure uranyl nitrate was introduced into the precipitation vessel that you can see in the bottom left, along with oxalic acid, and they were trying to produce a uranyl oxalate trihydrate slurry. Astera was used to keep the mixture homogeneous and stop the slurry from building up at the bottom. During vacuum filtration, where it would go up to the holding vessel, through the filter vessel into the filtrate receiving vessel, a batch of uranyl oxalate trihydrate slurry was observed going into the filter vessel, and then as it dropped down, there was basically a violent release of gas and the ejection of precipitate onto the glove box floor. So ill-advised, the operator picked up the slurry with his hands and put it back into the filter vessel, and obviously he felt ill quite quickly. And gas and vapor was released for a further 10 minutes or so until enough of the solution had been ejected that the transient stopped. So after taking apart the filtrate receiving vessel, they actually found a thin, hard crust of U-235 there, which had built up over a long time. So for this incident, the fission yield was about 10 to the 17, with 1 fatality and 5 exposures to other people working in glove boxes nearby. And this accident shows the importance of understanding slurry motion and how the buildup of solids can occur when the slurry is perhaps too concentrated or the flow of the slurry isn't quite enough. And it also indicates that the violent response of a slurry-based criticality excursion in a slurry-based system, specifically with the ejection and radiolytic gas creation that forced the slurry out of the filter vessel and all the way onto the glove box floor. Second accident I'll talk about, it was once again in Russia in November 1965 at a conversion facility that was responsible for converting low-enriched uranium hexafluoride into uranium oxide. So at this facility, uranium oxides were collected in this conversion hopper that you can see in the top left, and they were transferred via vacuum through to the accumulation hopper. At this point, the vacuum would be switched off, and the powders would simply sediment into this 20-litre vessel. However, during the time of the accident, or typically there are 2 filters, you can see a primary and secondary filter there, but at the time of the accident, it was found that due to operational mistakes, the primary filter was missing and the secondary wasn't fitted correctly. And this meant that when the vacuum supply was switched on, a large amount of uranium oxide slurry entered the vacuum system, building up large volumes, specifically in the vacuum supply vessel that you can see in gray at the bottom of the image. So interestingly, this only actually resulted in a criticality excursion when the vacuum was switched off, because it caused the uranium oxide to sediment to the bottom of the vacuum supply vessel. And also the excursion also quenched itself because of the ejection of the slurry to other parts of the system. And once again, this just highlights that that the changing geometry of the powder in the system can cause a nuclear criticality excursion, and it's important to consider these kind of scenarios. A couple other processes.
Greg, sorry to interrupt. The sound quality is a bit rubbish. I wonder if you could try turning your camera off, just attempt to try and improve that.
Sure.
If it's not possible, don't worry, but thanks.
Is it something better?
I'm sure it will be. So sorry to interrupt.
No, that's fine. That's fine. Sorry if the quality is not great. So yeah, a couple incidents that have occurred in processing facilities with fissile powder systems, Framatome and Global Nuclear Fuels, both occurred in cylindrical-based containers holding powder, which had these double contingency measures I discussed earlier with the moderating insert, as well as the subcritical packaging limits. And in both of these cases, it was either the powder was above the subcritical packaging limit or the moderating insert was missing. So moving on to, so I'll just highlight a bit about phenomenological modeling, which is what my research is focused on. So I generally look at 3 different steps when creating my phenomenological model. The first step was to examine the problem. So this is where I'll look at the specific physics that might be going on behind what governs the criticality excursion and what may quench it. So you can see in the image here, this is an example of a sedimentation phenomena occurring. So you've got dispersed particulates in some medium and they're getting concentrated at the bottom as they settle. The second would be to consider physical processes that are acting. So For the sedimenting system, this may be sedimentation, obviously. If there's any kind of nuclear heating, then you need to take that into account. Convection, boiling, those kind of processes. And the third stage is to actually develop coupled models. So this, in the image here on the left, you can see obviously a convection process, and on the right, Stokes' law corresponding to a particle settling in an infinite medium. So the advantage of using phenomenological models is that it's quite a process-driven approach, which means that it's quite easy to perform parametric uncertainty analysis. You can just change this parameter and see how that affects the model as a whole. Also, the coupled structure enables modeling quite complex systems with a lot of different processes. It does require a lot of consideration when selecting valid correlations, because ultimately the correlations are quite prominent in governing how the criticality excursion may go down. But it tends to be a bit quicker than the high fidelity full Navier-Stokes simulations, because it doesn't require the solution of the Navier-Stokes momentum equation. And also turbulence is generally implemented through correlations, so there's no need for complex turbulence models either. So just before moving on to the specific case that I looked at with regards to powders becoming wetted, leading to criticality excursions, I'll just talk about an experiment or 3 subcritical experiments that occurred at the Selen facility in Val-d'Uc. So these are very close to the physical scenario that I've studied. And the first experiment looked at the infiltration of water into a bed of 5% enriched powder at a rate of 0.5 liters per second. So you can see the image on the right there, that at planes located axially down the vessel, a set of water penetration detection sensors were put in, so you could monitor where the water was as it entered through the top. And they found that an almost linear infiltration rate into the powder could be seen, and they also observed a considerable amount of volumetric slumping. Second experiment investigated nuclear heating, where a sample of powder was placed in the post-Selen reactor and bombarded with neutrons. So the nuclear heating of the powder and surrounding water showed that there was a quasi-perfect exchange of thermal energy between the powder and water, which is something I'll discuss a little bit more later with the results of my work. And the third experiment was an electrical heating of a large sample of powder up to boiling point to investigate how powder dispersed due to gas production, similar to what we saw in the actual accidents in Russia, where the powder dispersion led to it actually being ejected from the vessel. So the specific case I'm looking at is the infiltration of water from a fire sprinkler system into a dry powder drum, which doesn't contain a moderating insert and is above subcritical packaging limits. So you can see in the image on the left, the typical infiltration sort of how the wetting front progresses, as well as the pooled water on top, how that changes. Where the green is wetted powder, the sort of orangey color is the dry, and the blue on top is the water. And on the image on the right, in this case, for some reason, the yellow is the wet powder and the green is the dry powder, and the blue on top. So this is a case that was proposed by the IAEA, JAEA, as well as the IRSN. And it's similar. So the 500 kilograms of 5% enriched UO2 at a bulk density of 1600 kilograms per meter cubed, which is wetted at 0.5 liters per second. This is very similar to the Selen subcritical experiment, so that I could compare with what data that they did show. And I consider 2 powder diameters of 110 microns. So some of the phenomenological processes to consider are written there. Firstly, the water infiltration that drives the transient by adding reactivity to the system and thermalizing neutrons in the interstices between powder particles so that they're scattered back into powder particles will greatly increase the number of fissions that occur. And this is what drives the criticality excursion. I also needed a model of neutron kinetics, which I'll describe a little bit in a few slides. And also a model for the reactivity feedbacks, which govern how the transient behaves and quenches over time. And for this, I needed to develop models for nuclear thermal hydraulics, radiolysis, boiling, and steam production. So for the water infiltration model, I simply use a Darcian flow approach. So the specific equation I use for unsaturated powder beds is the Green-Abbott equation. And I carried out a set of simulations for the powder bed that I described earlier with varying powder size, and you can see the results on the image on the left. And I compared it with the experimentally derived data from the Selen subcritical experiments. And I've been able to find good agreement with the infiltration time for powders which are sized between 9 and 10 microns, which corresponds well with the powder size that we would see in real life, based on the literature that I've looked at. On the right, you can see how the effective multiplication factor varies as the powder bed is wetted. So it goes from initially dry at 0.25 or so, all the way up to about 1.2, just above 1.2, which corresponds to a huge range of reactivity from the critical point at 1 up to 1.2. With the specific beta effective that we have for this system, the actual reactivity inserted was about $30, which obviously corresponds to a very large reactivity excursion and probably quite a violent response from the system. So for the neutron kinetics, I used just a point neutron kinetics model coupled with a multi-group neutron diffusion code to establish the neutron flux distribution or power shape to determine where the thermal energy is created within the system. So from simulations carried out in a quasi-steady state way, on the image in the left, you can see that as the bed immersion fraction increases, the peak neutron flux decreases and shifts across. And this peak corresponds pretty much exactly with the center of the wetted powder region that you can see on the right. As that goes down, the peak also tracks it, which is, I suppose, what you would expect. So for nuclear thermal hydraulics, I had to consider a number of different processes. So I looked at fission energy deposition, interfacial heat transfer through processes like convection, conduction, radiation, oiling, as well as advection and mixing. The model that I've used uses phase-specific thermal energy equations. So it means that I can model the powder and water temperatures independently. And you can see from so this is a result of the criticality transient for the 100 micron case as the powder bed is wetted. You can see there's a big peak in the initial power, which plateaus for a bit, and then drops once again. And you can see, I'm going to show an animation now in the image on the left. The blue represents dry powder, and then the wet powder is like the green, and the red is the solution or the water in the powder. So you can see that. So you can see that the bed slowly becomes saturated, and you can see that the green dots and the red line are pretty much right on top of each other, and that highlights the local thermal equilibrium between the phases is predicted for this model, which is very similar as the conclusion made in the Selene experiment, where they stated that there was a quasi-perfect heat exchange between the powder and water. So it sort of supports that finding. Onto the 10 micron case, you can see that there's a lot more of a violent response to this in this system. So once again, the power peaks, it plateaus, and then you see this slightly oscillatory response before the drop in power, and then further oscillations, which are effects of gas production, which I'll describe in a little on the next slide. So in this animation, you'll see something quite interesting, I think, at least. So you'll see almost a very sharp interface be developed between the dry powder and the wet powder and the pool water. And this occurs because the specific heat capacity of water is about 4,200 joules per kilogram per Kelvin, whereas the specific heat capacity of uranium powder is about 270. So the dry powder is able to, not as much energy is required in the dry powder to raise it to a certain temperature than for the wet powder because of the great heat exchange, effective heat exchange between the wet powder and the pooled water. So more energy is required to raise the wet powder and poor water temperatures. The conduction between the dry powder and wet powder isn't enough to sort of decrease the amplitude of this sharp interface because the thermal conductivity of uranium dioxide is quite low. And that, coupled with the porosity that I've considered in my system, which is about 0.845, means the area for thermal conduction is also low, just adding to the sharp interface. Finally, we'll look at some radiolysis boiling and steam production. So you can see for the 100 micron case, the plateau in the power occurs as radiolytic gas is created in the system, which you can see on the left 3 images on the bottom. So radiolytic gas is created, which introduces a negative reactivity in the system, which matches the positive reactivity introduced into the system by wetting, and this causes a plateau, which is something that isn't seen in solution-based systems. So it's quite unique to this, to powder systems. Then you see the big drop in power, which corresponds to the onset of boiling of the pore water, and large volume of gas is created, or steam is created, which causes the power to drop and then go up and continue to drop. For the 10 micron case, a similar response is seen, where you see the plateau in the power due to radiolytic gas matching the positive reactivity due to wetting. And then steam begins to be produced as the boiling point of the water is reached in the pores. And this causes an oscillatory response because of this interface between the dry and wet powder, where water hits the dry powder, it rapidly boils off, negative reactivity is inserted to the system.
I don't know if anyone can hear me, but I've suddenly lost all sound.
Oh, I can hear you. I don't. Can you hear me?
I can hear you both.
Yeah, generally you're okay, I think.
Hello?
Greg, if you're able to, can you carry on?
No, I can't hear.
Greg, it's Paul Sellin here. Are you able to hear me?
Oh yeah, I can hear you. Can you hear me?
Yeah, can you carry on, please? I think it's generally fine.
Okay, sorry about that. Yeah, so you get this oscillatory response because the gas obviously advects from the dry powder, and then more water enters it, which causes the gas to advect, and it just becomes a repeating process. And this is one of the conclusions anyway. So as I've shown, powers are found throughout the fuel life cycle from mining through to reprocessing, and it's important to be able to model nuclear criticality excursions in these kinds of systems. I've shown a phenomenological based model, which has been able to predict peak power and fission yield in a powder system undergoing wetting, as well as show how boiling contributes significantly to actually quenching the transient. I've also been able to show that the infiltration of water into the powders, it can cause huge variations to the reactivity of the system and result in about $30 for the system that I looked at least being inserted post K equals 1. A plateau in the power is seen due to the matching between the negative reactivity from radiolytic gas and the positive reactivity due to the water infiltrating. And this obviously is something that's quite unique to the powder systems when compared to solution-based systems. And obviously, since there are no large heat sinks in the system, large voids do get created to take into account the large reactivities, and thermal feedback alone doesn't really do much with regards to stopping the transient. Voids are created which stop it. Yeah, so thanks. I hope you could hear me.